Hi, welcome to your Unit 3, Lesson 2 notes. Today we're going to be getting into specific trigonometric functions of sine, cosine, and tangent. So what do engineers, artists, airline pilots, carpenters, and golfers have in common? They all work with angles like we all do from time to time. There are times we can estimate an angle like a golfer on his tee shot, but a carpenter or an engineer must measure angles precisely in order to be successful. Our chapter begins into the journey of trigonometry with an introduction into angles and their measures. In this lesson, we're going to examine properties of angles and their measures. So, when we are talking about an angle, we're going to be talking about an angle specifically being in standard position. Okay, back to it. So, standard position is an angle whose vertex is at the origin. It's has one of its sides on the x-axis, which we call the initial side. And then the terminal side is the side that moves around to create the actual angle. So this right here would be your terminal side of the angle. So coterminal angles are two angles in standard position that have the same terminal side. So one thing to note, when we are moving our angle in the up direction, we call that a positive angle. And if I were to move my angle in the clockwise rotation, so going this way, then that would be a negative angle, and it would have a negative sign in front of our numbers. So if you have a negative degreed angle, that means that it's just going in the clockwise rotation instead of the counterclockwise rotation. Okay, so now on the bottom there, we have what's called the unit circle. And your unit circle, one other thing, we use the Greek letter theta often to represent our angles. So if you see a circle with a line through it, that's our theta, and that's going to be our unknown variable. Instead of using x, we're going to be using theta for our angle. Okay, so your unit circle is down here. We're going to make our unit circle right here. And your unit circle is a circle whose radius is 1 unit and its center is at the origin. So if my center here is at 0, 0, and we go out 1 unit, then that ordered pair out there is going to be at 1, 0. Going up would put me at 0, 1. Going to the left would put me at negative 1, 0. Going down would put you at 0, negative 1. And then these points on the circle as it continues going around are all periodic, right? Because my y values would just keep repeating themselves as I go around. So a coterminal angle would be an angle. Oops, couldn't bring that back. So if I put an angle, let's say here, and I did one rotation around, then I would get back to that original. If I did another rotation around, I could get back to that original. If I went opposite direction and went clockwise, I could get back to that. So your coterminal angles will end up looking the same on the unit circle. It's just that they might have gone through more cycles or more rotations. Okay, so two angles in standard position. Let's focus on these coterminal angles that have the same terminal side we call coterminal angles. We can find an angle that is coterminal to any given angle by adding or subtracting one revolution, which one revolution around a circle is 360 degrees. So for example, if we let one of our angles beta is equal to 36, then a coterminal angle to that 36 would be 396, and we got that just by adding 360. It could be 756, and we could get that by adding 2 rotations of 360. We could get to negative 324, which would be just subtracting 1 rotation of 360. And then if we did clockwise 2 rotations in the negative direction, so negative 2 rotations, or 2 rotations in the negative direction, would get you to the negative 684. So for example 1, let's sketch out where 220 degrees would be. So think about your 360s all the way around. Up here would be 90, here would be 180, down here would be 270. So 220 would lie down here in quadrant 3, right? So 220 degrees, we'll say theta is equal to 220 degrees. All right, so let's come up with one coterminal angle. So I'm going to do theta prime. We could do 220 plus 360, which would get me 580 degrees. Or another option, we could do 220 minus 360 degrees, which would get us negative 140 degrees. And I could get as many as I potentially would want to get, right? So probably the easiest one to sketch here would be the negative version. So negative 140 degrees would be theta prime, could be a coterminal angle, right? Because if I looped this way, my terminal ray, my terminal side would land on the same spot as the terminal side of a 220 degree angle. So if I wanted to come up with like a general form of all the possible coterminal angles, so theta prime could be equal to, start with our original, so 220 degrees, plus any full rotation in any direction. So we could do 360 k degrees, where k is an element of our integers. For example 2, we're going to start looking at how we can look at angles in standard measurement, or standard position, sorry. So we're going to find the measure of the given angles before, which are labeled in the little arrows. So for our first angle, we have our initial side here, terminal side here. We're trying to find this angle and how many degrees it is equal to. Because we are going in the upward direction, or the counterclockwise position, we know that our angle must be a positive number. And then we just have to figure out what it is. So from here to here is 180 degrees. We are eliminating 45 degrees. So to find our angle, we're just going to do 180 minus 45, which leaves us with 135 degrees. So our angle here is equal to 135 degrees. For part B, because we're going in the clockwise rotation, so we're going down, right? So we're going down, think about it that way. It's going to make it become a negative angle. So we know that from here to here is 90 degrees, and then we're just tacking on another 30 degrees, or sorry, not 90, my bad. Well, it'll be 120, right? But we're going in the negative direction, so it'll be a negative 120 degrees. So going down, I should have done that. So negative 90 and a negative 30, because we're going in the clockwise direction. So our angle there is negative 120 degrees. So if one full rotation is 360 degrees, how many degrees is in 1/4 of a rotation? Well, that would be 90 degrees. 1/2 of a rotation would be 180. 3/4 of a rotation would be 270. Okay, so now in example 3, we're going to start looking at what's called reference angles. And your reference angle is, given any angle in a standard position, your reference angle is going to be the acute angle formed by the terminal side of a given angle and the x-axis. Do lots of underlining there underneath the x-axis. So if we wanted to figure out what the reference angle is of this red angle, so if we think about the red angle in a whole, we're told that it's 210 degrees. I was going to say, where's that number at? 210 degrees is the whole entire angle. So my reference angle is going to be the terminal side of my angle, creating the acute angle with the x-axis. So I need to figure out how many degrees is this angle right there. So anytime we're trying to find a new angle based off of another angle, like coterminal angles, reference angle, we do that little prime there. So 220 degrees is the whole thing. We need to figure out how many degrees is it from here. So in this case, we're just going to do 210 minus 180, which tells us that our reference angle is 30 degrees. So our reference angle is 30 degrees. Okay, so let's move to example 3. So we're going to sketch in the angles in standard position, and we're going to find the reference angles. So 100, so here's 90, 180, 270, 360, quadrant 1, quadrant 2, quadrant 3, quadrant 4. So 150 degrees is going to lie in quadrant 2, maybe somewhere around here. So let's go ahead and label that. There's my 150 degrees. And so now we got to find the reference angle. Reference angle is going to be created by my terminal side and the x-axis. So we just need to figure out how many more degrees do I get to that 180 degrees. So my reference angle here is equal to 30 degrees. For part B, 315 is going to go all the way around down here to quadrant 4, past the 270 mark. So 315 degrees. So my reference angle is x-axis terminal side. So how many degrees is in here? So 360 minus the 315 tells me that my reference angle is going to be 45 degrees. Down at C, we're at negative 120. So we're going to go in the down direction, negative 120 degrees. So my reference angle is terminal side and x-axis. So how many degrees is that? So reference angle is going to be 180 minus 120, which leaves me with 60 degrees. And your reference angle will always just be positive, because we're not really caring about the direction there. I just want to know how many degrees it is between my terminal side and the x-axis. And then 140 puts us over here in quadrant 2, 140 degrees. So what's left over? 40. So my reference angle is going to be 40 degrees. Okay. So the moral of the story is, if we are in, so I don't know if you want to mark this in a margin somewhere. If we are in quadrant 1, your reference angle is going to be equal to whatever your angle is, right? Because it is already creating the acute angle between the terminal side and the x-axis. If you are in quadrant 2, so we're over here, then we're going to find our reference angle by doing 180 minus whatever angle is. If we are in quadrant 3, which is really the only funky one, there we're going to have to do our angle and subtract 180. So to get your reference angle, you're going to do your angle and subtract 180 to get back up to the top. And then if you're in quadrant 4, so quadrant 4, so over here, then my reference angle is going to be 360 minus whatever our angle is. Hopefully that makes sense. Okay. All right. Moving on. Before you take example 4, we're going to talk about different ways that we can measure angles. So far, we've been talking about measuring angles in degrees. Now we're going to talk about a second way that you can measure angles, which is what's called radians. So a central angle, if you remember from your geometry days, is an angle created with the vertex being at the center. So theta is a central angle. And then the intercepted arc is the arc that is created by the endpoints of that central angle. So here is my intercepted arc. Intercepted arc. Right there. Sometimes we use a lowercase s to represent our intercepted arc. And then a radian, so now here's new thoughts potentially. 1 radian is the measure of a central angle of a circle that intercepts an arc equal in length to the radius of the circle. You can use a proper notation to convert an angle measure from one unit of a measure to another. So if this is a radius of r, let's go down here, if that's a radius of r, and that's a radius r, and here's our theta, then this arc length is going to be equal to r also. We'll make it equal to 1. Okay? So now let's think about our circle and everything we know so far about a circle. We know that the circumference of a circle all the way around is equivalent to 2 pi r, or pi times your diameter, because your diameter is just double your radius. So now if we know that we have a unit circle where our r is equal to 1 in a unit circle, right? So now my r becomes 1, and I know that 1 full lap all around is equivalent to 2 pi, which is equal to 360 degrees. So 360 degrees is going to be equal to 2 pi. And then if I wanted to figure out what just 180 degrees was, then it would be equal to a pi. Does that make sense? So all the way around is 360 degrees. If my radius is 1, then all the way around would also be equal to 2 pi radians. Halfway around would be equal to just 1 pi radians if we're in a unit circle with radius being 1. Okay? So we can think about doing some conversions that way. So if pi is equal to 100 degrees, and that's equivalent to 1 radian, then I can do some conversions, and I can take my 180 degrees and divide it by pi to get whatever I think that that angle would be. And 180 divided by pi is about 57. So that means that our angle would be about 57.3 degrees. So 1 radian is about 57.3 degrees. So we're converting it. So if I go 1 radian around the circle right here, that's about 57.3 degrees around my circle. Okay. So when theta is equal to 1 radian, then we know that our radius is equal to our arc, which means our radius is equal to s. Right? Okay, so we can convert back and forth between radians and degrees, kind of using that philosophy. So we said before, when I converted from radians to degrees, we just had to do 180 degrees and divide it by pi. So I can convert whatever I have for radians and multiply it by the ratio of 180 divided by pi. And then we can do the reverse and go from degrees to radians by doing the reciprocal of it, which would be pi over 180 degrees. So if I want to get rid of the degrees to go to radians, I need to divide out the degrees. So I need the 180 degrees to be in the denominator. If I want to convert to radians, I need to divide out the radians, which would be the pi part, and divide by pi so that I'm left with the degrees in the numerator. So let's do some conversions. Find the radian measure of 60-degree angle. So a 60-degree angle, to go to radians, I want to divide out the degrees. So I'm going to divide by the 180, multiply by pi, which gets me pi over 3. And we leave radians with pi's in them instead of going to the decimal versions. So I would just leave my answer as that. Converting 85 degrees to radians, we're going to do 85 times pi over 180, which is 17 pi over 36. And then 2.5 radians to degrees, so now I need to divide out the pi to get rid of the radians and bring back the degrees, so multiply by 180, which gets us about 143.24 degrees on when we multiply that through. So some common radian measures that we can work with, other than like our normal 2 pi, is if we go a negative quarter of a pi, that takes us down a quarter of the way between 0 and negative 90, right? So this would be negative pi over 4 would be here. And we're going down, remember, because of the negative in front of our angle. Half a pi radian is going up here, so half a pi radian would be this angle at 90 degrees. 1 full pi of a radian would be our straight angle at 100 degrees. So remember, positive means we're going up, positive we're going up, negative we're going down. Okay, so complete each of the following using radian angle measures. How many radians is each angle of an equilateral triangle? Well, an equilateral triangle, each of those angles are 60 degrees. Converting to radians gets us 1/3 of a pi. The minute hand of a clock travels how many radians in 15 minutes? Well, 15 minutes, so we're starting here, going here. So that'll be 90 degrees. So 90 degrees times pi over 180 is equivalent to half a pi. The minute hand of a clock travels how many radians in 10 minutes? So 10 minutes out of 6, so 10 out of 60 would be 60 degrees, right? So 60 degrees divided by pi, or multiplied by pi over 180, gets us to pi over 3. Okay, so for example D, the minute hand of a clock travels how many radians in 5 minutes? So we have to figure out what fraction is 5 minutes out of the whole hour. So 5 out of 60 gets us 1/12. So 5 minutes is 1/12 of the whole rotation. If the whole rotation is 360 degrees, that means 30 degrees would be equivalent to the 5 minutes. So converting that to radians, pi divided by 180 gets us pi over 6 radians. And then part E, what is the measure of theta in radians? So if x is 45 degrees, then all of that red would be 360 minus 45, so 315 degrees. So if theta is 315 degrees, converting to radians, pi divided by 180, so 315 divided by 180 is 7/4, so 7/4 pi. And for F, what's the measure of theta in radians? So together, I guess we gotta solve for x first, so 5x and x should make 180 degrees. So that gets us 30, right? 180 divided by 6 is 30. So that means x is 30, which means theta is 150 degrees. Converting it, so pi over 180, 150 divided by 180 is 5/6 of a pi. All right, because remember pi is half of a circle, so 150 degrees would be 5/6 of a pi. Okay, here ends part A.